As a student, it is very important to have a fresh morning in order to have an energetic and efficient day. Most of us use alarms to wake up because we have a certain routine of day which provides us enough sleep. But sometimes when your alarm is at 10 a.m. and you actually wake up at 8 or even earlier, and since you're already awake, it is somehow hard to fall asleep again. This happens because the blinds in our room cannot block out all the lights, and we are awakened by the bright light in our room. This is because light influences our internal clock through specialized light-sensitive cells in the retina of our eyes to help us tell whether it's daytime or nighttime. Light is very important during the whole day. It's like a mood maker. Such as the bright light will be able to help people keep awake and alert, and dim light provides a relaxing environment. According to the things discussed above, we came up with the idea that if we can invent a smart blinds which can provide you a fully dark sleeping environment and also are smart enough to automatically adjust the mode to provide different lightiness in our room, we will be hopefully have a more efficient day. Our blinds is designed to work in 3 different cases controlled through the app in the user's phone. The first one is provide no light coming from the outside during the sleeping time. The second one is adjusting the amount of light coming in according to user input. For example, if the user is having a coffee and want to relax by having a dim light, it can simply use the app and choose to close the blinds a little bit. Our blinds will change the angle and dimmer the light. The third one is adjusting the amount of light coming in automatically according to a user set schedule. Like if the user wants to wake up at 10 a.m. and he set to open the blinds at 9:30 tomorrow morning, our blinds will be able to gradually open itself at 9:30 tomorrow morning. Our overall objective is by adjusting the nightness in our room through our smart blinds to make our life easier and more efficient.
The mechanical component of this project focused on the construction of 4 main pieces. On the picture on the left, the detailed drawing for a motor coupling is shown. This first coupling was going to be used to attach the motor to the blinds rod, so to control the slate's angle. The next picture shows the detailed drawing of the motor blackout curtain coupling. This coupling was 3D printed in time, and pictures of it will be later shown. It is worth mentioning that this coupling was successfully tested. On this slide are the detailed drawings of the 2 other pieces. On the left drawing, there is a motor bracket for the blackout curtains motor. This bracket will have encased the motor and then be drilled on the wooden frame side. The next drawing shows the wooden frame. Length and width measurements from the blinds and the blackout curtain were taken to design it. Inside the frame, both the blackout curtain and the blinds were to be secured to the frame sides. In the back part, blackout curtain, and in front of it, the blinds. On the back and front inner side of the frame, the electrical circuit of the project was going to be attached. For the blinds, 2 wooden square pieces were attached to the frame sides, so that they could act as platforms to which the underside of the plastic U-shaped header of the blinds could be drilled into.
Now I will talk about the electrical hardware. For the board, we choose ESP8266 Wi-Fi board because it can give any microcontroller access to the Wi-Fi network. This can help us to complete the function of using mobile phones to control curtains. For the motor, since we decided to use only one motor to adjust the curtain and the other one to adjust the blind, so we choose the motor with a high torque. Relay is a switch that can help to open and close the circuit. It is connected between the motor and the lighting element. Motor driver is connected between the motor and the board. It can take a low current control signal and turn it into a higher current signal that can drive the motors. The last one is light sensor. This sensor is directly output in the light intensity unit, lux. And that means we don't need to do extra calculations.
The control of LED light, blinds and blackout close is mainly controlled by Snow switch. The user control page includes 3 main pages: light control, blind control, and the blackout close control. First, about the light control page. In the default state, when the user presses the button when the button display is on, the LED light is on, and when the button display is off, the LED light is off. In addition, the user can also set the length of time the LED light is turned on in the timer. Regarding the blinds and the blackout close, the control method is similar. Adjust the buttons on the page to control the motor to control the angle and the blackout close up and down. Select the upper right corner of the box to adjust the control model of the switch. That is from collecting to long pressing. That is when the button is held on, the motor runs, and the button is released, the motor stops. Therefore, the user can precisely adjust the intensity of the light entering the room as required. In this slide, the video about how our project working. In the first video, it shows turning on and turning off the light. In the second video, it shows how the directions of the motor is running. The different directions of the motor lead the blackout close up and down.
On the first two pictures on the left, the motor blackout coupling can be seen already attached to the blackout curtain. On the next picture, the wall attachment that came with the blackout curtain, which was to be drilled to the wooden frame, can be seen, plus its corresponding coupling. On the picture on the top, it can be seen how the sides of the U-shaped plastic case have been partially cut. This plastic case serves as a header and it contains the blinds system. On the picture on the bottom, the blind systems can be seen more clearly.
One of the requirements we had to verify was that the blinds would operate under 30 decibels. This was important to us because for most people, anything above 30 decibels would wake the user up harshly and cause disruption to deep sleep cycles and overall affect your sleep quality. To test this, we used the decibel meter to measure the sound intensity at a fixed distance away. For us, this distance was 1.5 meters distance and 0.55 meters off the ground, which simulates the normal position of a bed according to a window. After some trial and error, we passed this test. We had to enclose the motors in a box to make sure that they would dampen the sound. Of the many verification tests that we conducted, another important one was to meet the requirement that the LED light-eating unit must illuminate 300 lux. This is important because it takes 200 to 300 lux on average to wake a person up effectively from their deep sleep cycle. Our testing method was to use a lux meter to measure the light intensity from the inside of the window. We did this under a completely dark environment to simulate a worst-case scenario where there is no outside lighting and the LED lights have to do all of the illumination. Our prototype passed this test after using a combination of 3 LED light strips. One of the user needs that was important to satisfy was ease of use. This means that user controls are easy to learn and really intuitive to use. So our test consisted of recording the time taken for new users to learn how to operate the blinds. This included how to raise, lower, and set the alarm functions for the blinds. A passing time would be 3 minutes. After running our tests, we discovered that our average learning time was approximately 2 minutes. Although it is important to note that not all of our functions are fully implemented in the user interface yet, so this test will have to be done in the future again. In the end, we were able to complete the individual functions of the smart blinds, which allowed for a proof of concept for our overall design. In regards to the automatic raising and lowering functions, we successfully programmed the motor's relative direction and degree of turn. The motor couplings to connect the blinds to the blackout curtains were 3D printed and pressure fit. Moreover, the prototype of the frame is dimensioned and ready for test fitting. One of the key functionality of the smart blind was to help users wake up in the morning by automatically raising the blinds at a given time. Working towards fulfilling that feature, we programmed the blinds to connect to a smartphone app called Blink through Wi-Fi, where the users can set up a wake time wirelessly. Furthermore, our verification and validation tests help work as a proof of concept as well, and in the future we'd like to pursue those tests that we weren't able to conduct.
The next step for our project would have been to assemble individual components of our smart blinds. This assembly process will start with mounting the motors and blinds to the wooden frame and then testing. Finally, the last step will be integrating the LED lights to the prototype. and make every component operate at the same time. Once assembly is complete, we will need to revisit the validation and verification test. For us, as a team, working on this project has been a tremendous learning and very enjoyable experience. Working through the engineering design process and the different designs in order to find the best possible solution was really fulfilling. We learned the value of reflection and analysis when drafting the possible solutions, and the value of communication and teamwork, especially in unfortunate circumstances, such as the current ones. Thank you.